Now let's start the next lecture again, which is on classification. And in the previous lecture, we were talking about how we can train classifiers or what kind of classifiers we have, the classical algorithms, where we discussed the max margin classifier, nearest neighbor classifier, and we also briefly looked into support vector machines. Now, there the idea was you have some algorithm which can extract like some kind of features from your data. And all those algorithms then will use those features to do the classification. All right. And of course, those features could be directly your pixel values if it's like a very small resolution image. But again, that's, you can say like that's kind of your algorithm, right? To extract features. So they assume you have features, and you can't just operate on like the spatial structure of your image. So now we are moving on to like how we can actually do classification without extracting features. We want to do this like end to end. That's like a very common term used here in deep learning, or you can say like for neural networks. So the idea is you don't separate these two steps. You just have your sample or whatever input sample you have, data you have, and you solve this jointly by extracting features and then using those features to perform classification. Okay, so that's like a very big difference between the algorithms which were discussed in the previous lecture and what we are going to study now. And of course, this is something which we have already seen. Like I think the full lecture we have already seen in the course, like in different lectures. But I think there are a couple of concepts which will be new, and I will focus more on those. And Softmax is one of those. But most of this we have already seen, so I will try to quickly skim over those slides. All right. So classification, the idea is you have, let's say, multiple classes, in this case, 2 different classes. You want a decision boundary, right? And we saw like how we can learn this in a form of equation. And that equation is just a function. Now, again, in this case as well, we are going to learn the function. But as we do so, we will actually make use of like these samples itself. Okay, so it's going to be end to end. We'll not utilize features of these samples. So let me quickly go through the framework. As I said, whatever classifier you learn, you can represent that as a function, which will make predictions given an input image. In this case, it will be your input image. Okay, so you'll have training samples, which you'll use to learn this function. Once you have learned, you will evaluate that. Okay, so the idea here is this image features and this training, it's like a single step. So you'll directly use the images, and you'll have your model, which will extract features, and then those features will be used for making predictions. And the way it's done, like you have a cost function for each sample, it will tell you how good the model is doing. And then it will try to compare that with the ground truth or the label you have. And then it will penalize like your network weights. And that's how you train your model on your training samples. And once that is trained, you use that on the testing samples, and that will make predictions for you. Okay, so features, as I said, like there are a lot of different ways you can use features. But in this case, we are actually just, we're trying to learn features as we learn the classifier itself. So both of them are going to be happening together at the same time. Now, one simple way for doing that could be like you can build a neural network. You have seen this before. And what you can do is you can just transform your image to like a flattened feature vector. You did that for a programming assignment as well. And that will go as input to your neurons. And then your function is actually this transformation from neuron to neuron, how you're actually taking weighted average, or you can say linear combination of these neurons to generate future neurons, and finally to make the prediction. Okay. Then you have these convolutional neural networks. We have spent a lot of time understanding how these neural network works. So the way to use these for classification is, and that was our use case as well when we were talking about CNNs, you will take these images and you will have these convolution layers which will try to learn those filters, and those filters will extract features from your images, right? And that's basically pattern matching. It's trying to match the pattern of the kernel in the input data. And again, after a lot of such transformations, you will have like a final layer which will make prediction for you. And of course, this could be a fully connected layer, and we will see like one variation where we don't even need this fully connected layer. Okay, this is just one variation. So I think we are going to discuss one of that aspect where What if we don't have fully connected neural networks here? We just have CNNs, and can those CNN make these predictions for you? Okay, so that's a very interesting use case. All right, so the basic building block, that's these neurons. We know that it's just linear combination of your input, and these are the weights which are actually being learned. And each neuron actually predicts something, which is passed to the other neurons. And at the end, it's like the final neuron you have, which will make predictions for you. Okay, so all of this is a revision, and as we discussed in the last lecture, like if you have multiple classes, it was not that trivial for support vector machines. But in case of CNNs or neural networks, all you have to do is just add like additional neurons. So for each class, you can have a neuron, and you just use like output of that neuron as a way to estimate whether this particular class is present or not. So solving a multi-class classification problem is much easier in this case, which is a good news. And of course, like all of this is nothing. It's just transformation. It's just function, right? Function after function. And you have like composition of different functions in form of these layers, whether it's neural network or whether it's like CNNs for you. So every step, you're just transforming your data. Okay, so, and again, AlexNet, I think we spent like a sufficient amount of time understanding what this network is. So this was actually used for classification. Okay, so the idea was, given an image, it will make 1,000 predictions. So it's a n-way classification problem where n is equals to 1,000, which is like a way of saying you have 1,000 different categories in your training data. Okay, so all these parameters, I think we can skip because we already spent a lot of time in this.